When sizing conductors for a transformer, especially on the primary side, understanding the correct amperage calculation is crucial for safety and efficiency. In your scenario, a 2500 kV ampere transformer is being fed by a 12.4 kV system. The key is to differentiate between single-phase and three-phase power systems because the calculations differ. Given that we're discussing a transformer of this size, it's highly probable that this is a three-phase system which introduces the square root of 3 factor into the equation. The formula for calculating the primary amperage in a three-phase system is amperage equals kilovolt ampere divided by kilovolts times the square root of 3. Let's break this down. The kilovolt ampere rating represents the apparent power of the transformer, which in this case is 2500 kilovolt amperes. The kilovolts value represents the line-to-line voltage of the system, which is 12.4 kilovolts. The square root of 3 is approximately 1.732 and accounts for the phase relationship in a three-phase system. Using these values, the calculation becomes amperage equals 2500 kilovolt amperes divided by 12.4 kilovolts times the square root of 3. Performing this calculation yield amperage equals 2500 divided by 12.4 times 1.732, which is approximately 2500 divided by 21,4768. This results in approximately 116.39 amps. Therefore, the primary amperage is approximately 117 amps. First calculation you proposed, 2500 kilovolt amperes divided by 12.4 kilovolts equals 201 amps. This is the correct calculation only for a single-phase system. Applying this to a three-phase system would lead to an undersized conductor. Undersized conductors can overheat, leading to insulation damage, reduced equipment lifespan, and increased risk of electrical fires. Selecting the appropriate conductor size is not solely based on the calculated amperage. The National Electrical Code (NEC) provides guidelines and tables for conductor ampacity, which is the current carrying capacity of a conductor. Several factors influence the appropriate conductor size. Firstly, ampacity. The conductor must have sufficient ampacity to handle the calculated load current continuously. The NEC provides tables, such as Table 310.16, that list the ampacity of various conductors based on their size, insulation type, and installation conditions. Secondly, temperature rating. Conductors have temperature ratings that specify the maximum operating temperature. The ampacity of a conductor is based on its temperature rating and the ambient temperature. Higher ambient temperatures require conductors with higher temperature ratings or derating of the ampacity. Thirdly, derating and adjustment factors. The NEC requires derating or adjustment of conductor ampacity under certain conditions, such as when multiple conductors are bundled together or when the ambient temperature exceeds a specified value. These factors reduce the allowable ampacity of the conductor. Fourthly, voltage drop. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment malfunction and inefficiency. The NEC recommends limiting voltage drop to 3% for feeders and 5% overall. Fifthly, termination temperature. Equipment terminations such as circuit breakers and transformers have temperature ratings that specify the maximum temperature at which the conductor can be terminated. The conductor must be sized so that its ampacity is not greater than the termination temperature rating. Sixthly, conductor material. Conductors are typically made of copper or aluminum. Copper has a higher conductivity than aluminum, so it can carry more current for a given size. Aluminum conductors are less expensive but require larger sizes to carry the same amount of current as copper conductors. Considering these factors, you would consult the NEC tables to determine the appropriate conductor size for 117 amps. You'll need to consider the insulation type, the ambient temperature, and whether any derating factors apply. For example, if you are using a copper conductor with THHN insulation in an ambient temperature of 30 degrees Celsius, Table 310.16 of the NEC would be consulted. According to the NEC, 1/0 copper conductors are commonly rated for around 150 to 170 amps, depending on the temperature rating of the insulation. Even the calculated amperage of 117 amps, a 1/0 copper conductor would appear to be adequately sized. However, you must account for any dirting factors that may apply. If the conductors are installed in a conduit with other current carrying conductors, dirting factors may reduce the allowable ampacity. For instance, if there are 4 to 6 current carrying conductors in the same conduit, the ampacity must be derated to 80% of the value listed in Table 310.16. In this case, the adjusted ampacity of the 1/0 conductor would be 80% of its listed ampacity. For example, if the 1/0 conductor is rated for 150 amps, its derated ampacity would be 120 amps, which still exceeds the 117 amps requirement. Aluminum conductors have different ampacity ratings compared to copper conductors. Aluminum conductors typically require a larger size to carry the same amount of current as copper conductors. Consult Table 310.16 in the NEC for the appropriate ampacity ratings for aluminum conductors. If aluminum conductors are used, ensure that the terminations are rated for use with aluminum conductors. Bimetallic corrosion could occur when dissimilar metals, such as copper and aluminum, are connected directly. Special connectors and termination methods are required to prevent corrosion. If the conductors are exposed to high ambient temperatures, the ampacity must be derated accordingly. Table 310.16 provides correction factors for ambient temperatures above 30 degrees Celsius. Apply the appropriate correction factor to determine the adjusted ampacity. Voltage drop is an important consideration when sizing conductors, especially for long distances. Excessive voltage drop can cause equipment to malfunction or operate efficiently. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. To calculate voltage drop, you need to know the conductor length, the load current, and the conductor impedance. Use the following formula to calculate voltage drop. Voltage drop equals 2 times the length in feet times the current in amps times the impedance in ohms per foot divided by 1000. The NEC provides tables with impedance values for different conductor sizes and materials. If the calculated voltage drop exceeds the recommended limits, increase the conductor size to reduce the voltage drop. In summary, the correct amperage calculation for sizing the conductors to the transformer for a 3-phase system is amperage equals 2500 kV amperes divided by 12.4 kV times the square root of 3, which equals approximately 117 amps. Therefore, the correct conductor size based on the calculation is 1/0. However, it is critical to verify this selection against the NEC ampacity tables considering temperature ratings, dirting factors, and voltage drop to ensure a safe and code-compliant installation. If the initial calculation of 201 amps were used, then a 250 kcmil conductor is required. This may cause difficulty terminating the conductor into the transformer or switcher due to the physical size of the conductor. Remember to always consult the latest edition of the NEC and local electrical codes for specific requirements and to ensure compliance. Improper conductor sizing can lead to dangerous situations, so accuracy and adherence to regulations are paramount.